Today we're going to be talking about how to find direction cosines and direction angles of a vector. And in this particular problem, we've been given the vector I minus 2j minus 3k. Now, keep in mind that the first thing we want to do is find the direction numbers of the vector, and that's why we're going to be looking for direction cosines and direction angles. We're going to be dealing with direction numbers. So really, that's just as easy. If you have your vector in the form where you've got I, j, and k, you just want to take the coefficients on I, j, and k to get the direction numbers. So what this comes out to be for direction numbers, the coefficient on I is just a positive 1. The coefficient on j is a negative 2 when we include the sign here, so that's a negative 2. And the coefficient on k is a negative 3. Those are our direction numbers. Now, keep in mind that you can do the same thing if you don't have I, j, and k. You have, for example, x, y, and z. If we had something like x minus 2y minus 3z equal to 8, we could take this and get the same direction numbers. Again, we just take the coefficients on x, y, and z, and we'd end up with these same direction numbers, 1, negative 2, and negative 3. As long as your function is in this form where you have x, y, and z equal to some constant, you just take the coefficients on x, y, and z, and you get your direction numbers. Once we have our direction numbers, this represents a vector. It represents a vector that starts at the origin with an initial point at the origin of 0, 0, 0, and goes out to a terminal point of 1, negative 2, negative 3 in three-dimensional coordinate space. So this is a vector. We have 2 points on the vector, 0, 0, 0, and 1, negative 2, negative 3. We can use those 2 points to find the length of this vector or the magnitude of this vector. The way that we do that is using the distance formula. Let's call this vector vector A, and then we'll use our distance formula, and the distance or the length of the vector we'll call d sub A. And remember that the distance formula, when we are looking for the distance between 2 points in three-dimensional coordinate space, we just take x sub 1 minus x sub 0 and square it. Add to that y sub 1 minus y sub 0 and square it, etc. Think of this vector as 2 points, 1, negative 2, negative 3, and 0, 0, 0. So our distance formula will just be 1 minus 0 squared plus negative 2 minus 0 squared plus negative 3 minus 0 squared. And when you have a vector with the direction numbers like that, what of course you realize is that the vector is always going to be from the point 0, 0, 0, the initial point 0, 0, 0, out to this terminal point. So really, you don't even need to think about the initial point because subtracting 0 from each of these doesn't really change anything. What you can see, if we simplify this, we just get 1 squared plus negative 2 squared plus negative 3 squared, which is really just our direction numbers. We didn't even include the initial point 0, 0, 0. We can just take our direction numbers here from our vector A, 1, negative 2, negative 3, square each one of them and take the sum and then the square root of that sum. So what we end up with is the square root of 1 plus 4 plus 9, which of course is just going to give us the square root of 14. The square root of 14 is the length of our vector A. That's all we're going to need to find the direction cosines and the direction angles. At this point, it's really just a matter of writing out our answer. So our direction cosines, here's what that's going to look like. We're going to say cosine of alpha is equal to the x coordinate from our vector here, which is positive 1, divided by the magnitude or the length of our vector A, which is root 14. So root 14. Cosine of beta, and we always use the same variables. We're going to use alpha, beta, and upsilon. Some people pronounce it upsilon, but I hear it most often as upsilon. We'll see what the character looks like in a second. But alpha and then beta. For cosine of beta, we're going to take the y coordinate essentially from our vector here, the y component, negative 2. And we're going to divide that by the magnitude or the length of vector A, so root 14. And then we've got cosine of upsilon, which is going to look more or less like this, is equal to the z component, or really this k component here, negative 3 divided by root 14 again. These are the direction cosines. Now to find the direction angles, it's really simple. All we do is solve for the angles alpha, beta, and upsilon. And the way we're going to do that is by taking the inverse cosine function, or cosine to the -1, or arc cosine of both sides. That'll cancel this cosine on the left-hand side and leave us just with the angle. So these are our direction cosines. Our direction angles are going to be just solving for alpha, beta, and upsilon. So we're going to get alpha is equal to, we'll say arc cos, which is usually the cleanest way to write it, of 1 over the square root of 14. Beta is going to be arc cos of -2 over root 14. And upsilon is going to be equal to arc cos of -3 over root 14. Now we can leave them like that, but when we're talking about angles, it's usually helpful to get a decimal approximation of these values. And before we do that, it's really important to make sure that our calculator is set to degree mode. Normally the calculator should be set to radian mode, but in this case, when we're looking for an angle, we want to set it to degree mode. So set your calculator to degree mode and then take the inverse cosine function of 1 over the square root of 14, and we see that this is approximately equal to 74.5 degrees. If we do the same thing, we take the inverse cosine function of -2 over root 14, we see that this is about equal to 122.3 degrees, and that this one is about equal to 143.3 degrees. Now, if you're wondering what you've actually solved for here, these are the angles between the vector and the positive direction of the x-axis. So if I were to draw my vector in three-dimensional coordinate space here, if I have a three-dimensional coordinate system and I draw it using my right-hand rule where I have x, y, and z, and I say that my vector here starts at the origin, which is 0, and it goes out essentially to the point 1, -2, -3. So I would move out 1 along the x-axis, out along the y-axis in the negative direction, so -2, so that's going to be about here maybe, and then -3 along the z-axis. So if I go straight down in the negative direction along the z-axis, my point's about there. And we don't get a real clear picture of this in three-dimensional coordinate space, but it's about right there. So that's my vector. Finding the direction angles, alpha, beta, and upsilon there, gives me the angle between this vector and the positive direction of each axis. So 74.5 is the angle right here between my vector and the positive direction of the x-axis. So that's 74.5 there. If I write 74.5 approximately, the angle between the vector and the positive direction of the y-axis, and I can't illustrate this really well because remember, this is three-dimensional space. It's not just, parallel to each axis, it's on a different angle, but essentially the angle between this vector and the positive direction of the y-axis here is going to be 122.3 like this, and then the angle between this vector and the positive direction of the z-axis, if I just do that as a dotted line because it's kind of behind these two axes, but that's going to be about 143.3 degrees there. So that's what I found here when I find my direction angles, and that's how you find the direction cosines and direction angles of a vector.